In the vast expanse of our universe, where billions of stars and galaxies dance in a cosmic ballet, there exists a profound mystery, a gravitational titan known as the Great Attractor. This invisible force does not merely influence a handful of celestial bodies. It exerts a powerful pull on entire clusters of galaxies, revealing hidden dynamics and complexities that challenge our understanding of cosmic structure and evolution. Located approximately 150 to 250 million light-years away in the direction of the Centaurus and Hydra constellations, the Great Attractor lies within a region of space rich in galaxy clusters. Here, galaxies are not merely drifting aimlessly. They are drawn into a gravitational web that shapes their paths and interactions. The velocities of these galaxies, some racing toward the Great Attractor at speeds exceeding 600 kilometers per second, hint at the immense gravitational influence this cosmic entity wields over vast distances. The Great Attractor is a pivotal component of the Laniakea supercluster, our cosmic home, encompassing around 100,000 galaxies, including our Milky Way. The name Laniakea translates to spacious heaven in Hawaiian, aptly describing the vastness and interconnectedness of this supercluster. It serves as a reminder that our universe is a grand tapestry, intricately woven from the threads of gravitational forces, time, and matter. As we explore this region, we witness the interplay of cosmic forces that bind galaxies into clusters, filaments, and superclusters, forming a structure that extends across billions of light-years. At the heart of this mystery lies the Great Attractor, believed to be a colossal concentration of mass, predominantly composed of dark matter. This elusive substance, which constitutes approximately 27% of the universe, does not emit, absorb, or reflect light, making it incredibly difficult to detect directly. Yet, its presence is felt through its gravitational influence on visible matter. The dynamics of galaxies within the Great Attractor's grasp provide crucial clues, painting a picture of a massive gravitational well that is continually pulling them closer, shaping the very fabric of our cosmic neighborhood. As we delve deeper into this region, we uncover rich clusters of galaxies, such as the Norma cluster, which lies at the core of the Great Attractor. These clusters are vibrant ecosystems of cosmic activity, where galaxies collide, merge, and interact over billions of years. These interactions are not just destructive, they are transformative, leading to the birth of new stars and the recycling of stellar material back into the interstellar medium. Each collision releases immense amounts of energy, reshaping the very nature of the galaxies involved and contributing to the evolutionary narrative of the universe. Despite its significant gravitational influence, the Great Attractor remains shrouded in mystery. Observing it poses formidable challenges, as it is obscured by the dense plane of our Milky Way galaxy. The stars and gas within our galaxy obstruct our view, forcing astronomers to employ innovative techniques to study this phenomenon. Early observations in the 1970s and 1980s hinted at the existence of this gravitational anomaly, leading to an extensive series of studies that combined radio, optical, and infrared observations to piece together its elusive nature. Using redshift measurements, astronomers analyzed the wavelengths of light emitted by distant galaxies to determine their velocities. When a galaxy moves away from us, the light it emits shifts to longer wavelengths, a phenomenon known as redshift. By measuring these shifts, scientists can infer how fast galaxies are moving and in what direction, revealing the coordinated motion of galaxies toward the Great Attractor. This data paints a compelling picture of how the gravitational pull of this region shapes the motion of countless galaxies across vast cosmic distances. Gravitational lensing also plays a vital role in our understanding of the Great Attractor. When light from distant galaxies passes near massive objects, such as galaxy clusters, it bends and distorts, creating a lensing effect. This phenomenon allows astronomers to map the distribution of mass in the Great Attractor, including the unseen dark matter that dominates its structure. By studying the patterns of lensing, scientists can infer the gravitational influence of the Great Attractor and its surrounding mass, providing tantalizing glimpses into the hidden depths of this mysterious area. But the story of the Great Attractor does not end there. It is intricately connected to the broader narrative of our universe, woven into the fabric of dark energy and the expansion of cosmic space. While the Great Attractor exerts a powerful gravitational pull, encouraging galaxies to move toward it, the universe itself is expanding at an accelerating rate due to dark energy, which accounts for about 68% of the universe's total energy content. This interplay between the gravitational attraction of the Great Attractor and the repulsive force of dark energy raises profound questions about the ultimate fate of the universe and the fundamental nature of reality itself. Scientists continuously refine their models to understand how structures like the Great Attractor fit into the larger picture of cosmic evolution. Advanced simulations of cosmic structures provide invaluable insights into how gravitational forces shape the universe over time. These models suggest that the Great Attractor may be part of an even larger structure, the Shapley supercluster, further extending our understanding of cosmic hierarchies and the intricate gravitational web that connects galaxy clusters across the universe. The Great Attractor is a crucial node in the cosmic web, a vast network of filaments connecting clusters of galaxies. This web-like structure is formed by the gravitational attraction of dark matter, influencing the distribution of galaxies and clusters throughout the cosmos. Understanding how the Great Attractor fits into this cosmic web is essential for deciphering the evolution of large-scale structures and the fundamental forces that govern them. It serves as a reminder of how interconnected our universe is, where the motion of one galaxy can ripple across vast distances, impacting its neighbors and the structure of the cosmos itself. As technology advances, so too does our capacity to explore these cosmic mysteries. Upcoming astronomical missions and next-generation telescopes, such as the James Webb Space Telescope and the European Extremely Large Telescope, promise to unveil new insights into the nature of the Great Attractor and the role of dark matter in shaping our universe. These tools will allow scientists to probe deeper into the obscured regions of space, enhancing our understanding of the gravitational influences at play and revealing the intricate relationships between galaxies. As we continue our quest to explore the cosmos, the Great Attractor stands as a compelling reminder of the mysteries that still await discovery. In the heart of our universe, it challenges us to rethink our understanding of gravity, mass, and the very fabric of space-time. The Great Attractor is not merely a point on a cosmic map. It is a testament to the wonders that lie beyond our reach, inviting us to journey deeper into the universe's secrets and to confront the profound questions that define our existence. What lies beyond what we can see? How do the forces of attraction and repulsion shape the destiny of the cosmos? These questions beckon us forward, urging us to unravel the mysteries of the universe and to seek the truths hidden within the cosmic expanse.